We're going to look at one more example of testing for two population variances, and this time it's going to be a one-tailed test. So in this problem, we have two fast food chains. Okay. One fast food chain carried out a study to measure the variability in waiting time, okay, and defined as the time in minutes from when an order is placed and was completed and delivered. Okay. Order placement and then completed and delivered. Okay. What is the time and the variance of that time? Okay. And we want to look at two different time of day. Okay. Lunchtime and breakfast. So lunchtime we have a sample of 25 and the sample variance turned out to be 4.4, and breakfast is 21 sample size and the variance is 1.9, and we want to test whether the lunchtime variance is greater than breakfast time variance. So the lunchtime variance sample size is 4.4, so that turns out to be okay because that's the larger variance, so that goes in the denominator. So like this, sigma squared sub L, the lunchtime variance, is greater than sigma squared sub B, the breakfast time variance, and the opposite goes in the null hypothesis. So F statistic will be the ratio of the two sample variances. So let's head on down to Excel, head on over to Excel and complete the problem. So X sub 1 is wait time during lunchtime, and then sigma squared sub 1 is the variance of wait time, and then during breakfast and variance during breakfast. And now the alternative hypothesis is sigma squared sub 1 is greater than sigma squared sub 2, and H sub O then is the opposite of that. The statistics from the two independent random samples are given. Sample 1 size is 25 and the sample variance is 4.4, and sample 2 the size is 21 and the sample variance is 1.9. Now the sample sizes are not 30 or more, so we have to assume that the underlying population follows normal distributions. That's the assumption required. Now the degrees of freedom are n sub 1 minus 1, then n sub 2 minus 1 for the numerator and the denominator degrees of freedoms. And the F stat is sample variance divided by the second sample variance. So here we are not going to square this, so you have to be very careful. If the given information is standard deviation, then we square both numerator and the denominator. But here if you square, then you're going to be squaring the variance itself, and that is not correct. So you have to pay attention to that. What is the given information? If the given information is standard deviation, then you square it to convert it into variance. If the given information is variance, you don't have to do anything, you just simply take the ratio of the two variances. Now the critical value of F is, we can use F dot INV dot RT, and since this is a one-tailed test, we use alpha of 5%, and that's blank right now, so I'll enter. Okay, let's start with entering that 5%. So the critical value is F dot INV dot RT, and since this is a one-tailed test, we have to simply use alpha, not alpha over 2, comma the 2 degrees of freedoms. So that gives us the F table value. If we use the F table from the textbook, we would use the F tail area of 0.05 and the degrees of freedom of 24 and 20. So here is the F table. Tail area is 0.05, then 24 and 20 will give you 2.08. So which is what we have here. So the conclusion is, since F stat is greater than F table value, we reject the null hypothesis. So p-value approach, and we do F dot dist dot RT the F statistic, comma, the 2 degrees of freedoms. Okay, so that gives us the right side tail area, and this is a one tail test, so that's it. That's our p-value. So since p-value is less than alpha, we can reject the null hypothesis. Okay, and then provide an interpretation. So we have sufficient sample evidence to conclude that the variance of delivery time during lunch hour is greater than that during the breakfast time. And the probability that this is an error, the conclusion is an error, type 1 error, is 3.03%.